The whole idea of induction and induced current is related to the concept of moving charges creating magnetic field and magnetic field exerting forces on moving charges. But more broadly, it doesn't necessarily have to be that the charge is moving. It just has to be some sort of change happening. So a changing magnetic field can influence the charges in a wire, for instance. Or if you have a wire that's moving through a magnetic field or rotating in a magnetic field, under certain circumstances, that can cause charge to flow. It can cause current in the wire, almost as if there's a tiny invisible battery, even though there isn't one. And the way this works is largely built around this idea of magnetic flux. Flux is basically a measure of to what extent is a vector field, in this case the magnetic field, passing through the interior of some loop or piercing through some surface. For example, let's say you have a loop of wire, and I'm going to try drawing this in 3D because this kind of has to be three-dimensional. Let's say you've got a loop of wire. I'm going to draw it kind of donut shaped to exaggerate the idea that this end is closer to you and this end is further from you. So we've just got this loop of wire and we're holding it horizontally like this. So loop of wire. And we are going to have, let's say we have a magnetic field also. If we've got a magnetic field, let's say a magnetic field that is pointing to the right. Would you say this magnetic field is passing through the loop? No, it's not passing through the loop at all. It is, I guess you could say it is skimming along the surface of the loop, but it isn't really going through the interior of the loop. So this would be a situation where we would say there is no flux at all. Flux, again, representing the extent to which the vector field lines are passing through the surface, or through, in this case, the surface would be the region enclosed by the loop. I usually think of it as if you imagine taking this loop and dipping it in bubble soap, there's going to be a film of bubble soap enclosed inside this loop. That's the surface we're talking about, the surface enclosed inside that loop. In this case, though, the field lines are just skimming along the surface to not going through the loop. So that would be no flux. On the other hand, if we take that same loop and we have magnetic field, let's say we have separately, we have a magnetic field pointing straight up. In this case, would you say that the magnetic field is passing through the loop? Yeah, the magnetic field pointing upwards is passing through the interior of that horizontal loop. So we would describe this situation as lots of flux. So that means that even though these are largely the same situation, like let's say we have the same strength magnetic field, the exact same loop, it looks like direction matters a great deal here. And the way we describe the direction is based on the idea of a normal vector. Just like we did for optics when we were measuring the angle between the incoming ray of light and the vector parallel or perpendicular to the surface, the normal vector, we're going to do the same thing here. Because it's very mathematically inconvenient to try and measure the angle between a vector and a surface. So what we do instead is we create a normal vector, a vector perpendicular to the surface itself. Let's say we call that, usually called n hat. And instead of the usual vector sign, we draw this little, it's called a caret or a hat. This symbol usually just means this is a unit vector. It is a vector whose length is exactly 1 by definition. Likewise, here we would draw in a normal vector, a vector perpendicular to the surface whose length is exactly 1. We'll call that the normal vector. And note that you have two options for a normal vector. We could draw this normal vector pointing straight up or straight down. Either way ends up working mathematically, but it tends to make the most sense conceptually if you choose the one that agrees with the existing magnetic field. So I would choose an upwards normal vector in this case because that most closely agrees with the existing magnetic field. So that's the normal vector. In this case, with lots of flux, what's the angle between the normal vector and the magnetic field? If we've got magnetic field this way, normal vector this way, what's the angle between those two vectors? They're parallel, right? So yeah, the angle would be 0 degrees. Lots of flux because the angle, theta being the angle between the normal vector and the magnetic field, is 0. Whereas in this case, what's the angle between the magnetic field and the normal vector? 90. We get no flux because the angle is 90 degrees. In general, if the magnetic field is perpendicular to the normal vector, then that means it's just skimming along the surface, so there's no flux, no penetration through the loop. So no flux if the angle is 90 degrees, lots of flux if the angle is 0 degrees. And then anywhere between, you can get some flux. For example, let's say we have same loop, and we have a magnetic field that's along some diagonal. It is piercing somewhat through the interior of the loop, but not as much as it would if it was perpendicular to the loop or parallel to the normal vector. In this context, you draw in the normal vector. So we've got a normal vector n hat. We've got our magnetic field lines B. And we have an angle between them. This angle would be theta. It's not 90 degrees, so we do get some flux, but it's also not 0 degrees, so we don't get as much flux as we could. And because of this, because we get the most flux when the angle is 0 and the least flux when the angle is 90, we want to establish a trigonometric function that matches that behavior. What's a trigonometric function that's largest at 0 and 0 at 90? Exactly, cosine works perfectly here. So we're going to define flux in terms of cosine of the angle, theta being that angle between the normal vector and the magnetic field line. Also, what else do you think would influence how much flux there is? The extent to which the field lines are passing through the interior of the loop. Yeah, the area is going to make a difference. The larger the loop is, the more opportunities there are for field lines to pass through. So area makes a difference here. And yes, the strength of the magnetic field itself. Because the stronger the magnetic field is, the more closely packed the field lines are in the way we draw the diagram. And so the more field lines are passing through the interior. So all three of these quantities influence what we call flux. And we usually write this as the Greek letter capital phi. So the magnetic flux is defined as area times magnetic field times cosine theta. And more formally, we'd write it as an integral because you want to add up a lot of little pieces for the entire region. But assuming the magnetic field is constant throughout this entire region, you can just multiply area times magnetic field times cosine theta. Any questions on that so far? So the way this ties into induced current is that flux alone doesn't really do anything. Magnetic flux is just describing the state of the situation right now. Just the existence of magnetic flux doesn't do anything. But like I said earlier, if the magnetic effects are changing, that can cause electrical forces. So if there's a change in flux, if flux is changing as time passes, then that can cause the charges to move around. It can cause extra current to flow through this loop. And you can get a lot of insight into this based on looking at the units of measurement here. If you take a look at the units of measurement, for example, what is area typically measured in? Area, well, distance is measured in meters. Area would be measured in, yeah, meters squared, because you're multiplying a distance times a distance. And have you seen yet the units of measurement for a magnetic field? Yeah, capital T for Teslas. 1 Tesla being the unit of magnetic field. And 1 Tesla is actually a very large amount of magnetic field. Magnetic fields are going to be fairly small amounts of Teslas in a typical situation. And then cosine of theta is unitless, so we can ignore that. Magnetic flux is measured in Tesla meters squared. And have you seen how Tesla breaks down into simpler units yet? Do you have any other formulas relating magnetic field to other quantities you already know? Did you get a formula for how strong the magnetic force actually is? If you got a moving charged particle, magnetic force, like if you've got just a charged particle moving through a magnetic field, how would you calculate how strong the force on it is? Yeah, Q times V times B should work. The right-hand rule tells you the direction, but the usual formula for the amount of force is charge times speed times magnetic field, and also times sine of the angle between speed and magnetic field. So this will tell you how strong the force is. More magnetic field, of course, is going to lead to more force. Faster speed of the charged particle leads to more force. More charge on that moving charged particle leads to more force. And you get the most force if the angle is 90 degrees, because sine is largest at 90, and no force at all at 0 or 180. But if we take a look at the units here, we've got, as usual, force in newtons, charge in coulombs, speed in meters per second. And we're saying magnetic field is measured in Teslas. And then sine theta, again, is unitless. But this means that we now have an equation relating Teslas, this new unit of magnetic field, to these other units we already know about. So we can solve that for Teslas, and we get Teslas equals what? What do you get if you
isolate? Seconds per coulomb meter?
Yeah, newtons times seconds per coulomb meter. So this is what a Tesla is. A Tesla is a Newton second per coulomb meter. And on its own, that doesn't really seem very meaningful. It's just what the units have to be in order for this to work out right. But that means we can replace Teslas in the units for magnetic flux with Newton seconds per coulomb meter. If we actually fill that in, replace Teslas with Newtons times seconds over coulombs times meters, and then multiply by meters squared. What happens when we multiply that out? Yeah, one of the meters cancels out. And if we combine things a little further, we also have newtons times meters. Anyone remember from way back in 7A what newtons times meters is? If you got a force times a distance, what are you really calculating? That's work. In other words, a transfer of energy. So newtons times meters has to be joules, the unit of work. So we get joules times seconds over coulombs. And also one more conversion we can do. What's joules over coulombs? That's volts. That's the energy density idea. The energy per unit of charge. Joules per coulomb is volts. So that means the units of flux end up being the same as volts times seconds. So flux itself is not a voltage, but it is a voltage times a time. If we divide that by time, we get a voltage. So just by looking at the units, we can see that flux alone doesn't really have much meaning, but flux divided by time tells you an amount of voltage. So that's what the units tell us. The units tell us that flux over time is voltage, or specifically the rate of change, delta flux over delta time. So what this means is flux alone, just having an amount of flux doesn't really do much. But if the flux is changing as time passes, you get extra voltage in that loop of wire. And what's the usual way you would provide voltage in a wire? If you think back to the circuit stuff from 7B, how do you provide a voltage boost? Like, what would you have to include in that loop of wire to give it a boost in voltage? Like right now, this loop of wire doesn't have any current in it because there's nothing providing voltage. What other object would I have to install in this in order to provide voltage so that current would actually flow? Yeah, you got to have some EMF source, some electromotive force. The electrons are already there, but we need to push. We need the push of some voltage boost. What physical object provides that voltage push usually? Yeah, a battery. The battery in a typical DC circuit, the battery provides a plus delta voltage. It provides some extra voltage that causes current to flow. In this case, though, we can get voltage, extra voltage from a changing flux. So if the flux is changing as time passes, that change in flux creates extra voltage that acts almost like a tiny invisible battery, even if there is no battery in the loop. And of course, that only lasts as long as the flux is actually changing. As soon as the flux stops changing, you get no more voltage. And furthermore, the faster the flux is changing, the more flux changes per second, the more extra voltage you get, and the faster current will flow as a result. So that means if you want to know, is there voltage at all or not, do you get any induced, and this is usually called the induced voltage. Induced just means caused by or brought about by. So the induced voltage is just the extra voltage caused by the changing magnetic flux. So if the flux is changing as time passes, then you get extra induced voltage in the loop of wire. That extra voltage causes current to flow, even if there's no battery. So if you want to know how much voltage, you can take the derivative of this. The derivative of this, the rate of change of AB cosine theta, tells you how much voltage you get. So the extra voltage, usually written as delta V induced, or sometimes written as epsilon induced, the electromotive force, like from a battery, is the derivative of flux. In other words, the derivative of AB cosine theta. And it's possible that maybe all of these are changing, or maybe just one of them is changing, or two of them is changing. For example, maybe you're keeping the same magnetic field at the same angle, but you're just changing the area. Maybe you're making the loop larger or smaller. Even with wire that doesn't change length, you can change the area by smashing it flat to get a small area, or bending it out to more circular shape to get a larger area. So even just flexing the wire around is a changing area and therefore a changing flux if there's a magnetic field. Or you could keep the area constant but make the magnetic field stronger or weaker. How could you change the strength of the magnetic field there? Like let's say you just got a bar magnet and a loop of wire. How would you change how strong the magnetic field is? Yeah, if you move the magnet closer to the wire or further from the wire, yeah. Moving the bar magnet closer or further is going to change how strong the magnetic field is at the location of the loop, which is what we care about. Or you could keep the magnet where it is and move the loop closer or further. Changing where the loop is going to influence how strong the magnetic field is as well. So you can change the magnetic field strength by moving the magnet or moving the loop. Or alternatively, maybe the magnetic field is caused by current in some source wire. So if you change the current in the source wire that's creating the magnetic field, that also changes the magnetic field. So there are a variety of ways to change magnetic field. And likewise, the angle. Maybe you've got a magnet and a loop of wire. You could rotate the loop of wire and that would change the angle. or alternatively swivel the magnet around, that would also change the angle. So there are a variety of ways of changing any of these three values. If the total value of these is changing, then that means the derivative is non-zero, and therefore you get extra voltage. And that voltage causes current to circulate, based on the idea that delta V equals I times R. From way back in 7b, the voltage on a resistor, and you can treat the wire in the loop as a resistor, equals current times resistance. Figure out the rate of change in flux, that tells you how much extra voltage you get. Divide by resistance, that tells you how much induced current you get. Any questions on that so far? So to summarize what we've got so far, flux is area times magnetic field times cosine of the angle. It ultimately doesn't really matter whether there is flux or isn't flux, or how big the flux is or not. What matters is the flux changing? And if so, how fast is it changing? So if the flux is changing as time passes, you get extra voltage in the loop of wire, which can cause current to flow. The faster the flux is changing, the more voltage you get. We also really need to take a look at direction, because usually this formula is written as having an extra negative sign in it. Delta voltage equals negative derivative of flux with respect to time. This is usually called Lenz's law, or sometimes Faraday's law. Lenz's law or Faraday's law, one of those is the equation. The other one is basically describing what the negative means. But what that negative signifies is that the voltage creates current. The voltage is going to be in a direction to create current that is in a direction opposite to the change in flux. Not necessarily opposite to the flux itself, but opposite to the rate of change, opposite to the direction flux is changing. As a quick example, let's say you have a loop of wire in a downwards pointing magnetic field. So here's this loop of wire. And we have a magnetic field pointing downwards. And let's assume it's a uniform magnetic field. It's this same downwards vector everywhere. And so we just have this strong downwards magnetic field. And let's say as time passes, that magnetic field gets weaker. Getting weaker as time passes. And we want to figure out, does that cause current? And if so, in which direction? So we need to take a look at this in terms of flux. Flux, as usual, we're going to treat as area times magnetic field times cosine theta. And in this case, which direction would you say is the normal vector? Or which direction would we want to choose for the normal vector? If the loop of wire is oriented like this, first of all, what are our options for the normal vector? What would be perpendicular to that surface? Yeah, either upwards or downwards. Because we've got a horizontal surface, normal to that, perpendicular to that would be either straight up or straight down. So we could choose straight up or straight down as the normal vector. Mathematically, it works out the same either way. You just get some extra negatives that end up canceling out. But it's going to be making the most sense conceptually, I think, if you choose the direction that already agrees the most with the existing magnetic field. So I would choose a downwards normal vector. So we're going to use downwards as the direction of our normal vector because that agrees with the existing magnetic field. If you do choose upwards, you end up getting the same result because of some extra negatives that cancel out. but it's a lot more difficult to understand intuitively what's going on. So I would choose downwards as a normal vector here. In that case, there is area, there is a magnetic field. And what's the angle here between the normal vector and the magnetic field? 0. And cosine of 0 is 1. If we had chosen the other direction, we get 180 as the difference in the angle. Cosine of 180 would be -1, which is going to be annoying. So I would just keep it as a normal vector in the same direction as the magnetic field as much as possible so that the cosine stays positive as the result. Negative flux is, again, mathematically works. It's just annoying to try and figure out what's going on. So there is flux. But again, it doesn't matter whether there's flux or not. What matters is the flux changing? So is anything in this situation happening that suggests the flux is changing as time passes? Yeah, the magnetic field is changing. Specifically, the magnetic field is getting weaker. The area stays the same, the theta stays the same, but the magnetic field is getting weaker, which means the flux is decreasing. The flux decreases as time passes. The thing is, though, what we need to do in order to make sense of the negative sign in this equation, we need to take that decreasing flux and associate it with a direction. And this is kind of shady here because formally flux is a scalar. It does not have a direction. But in order to make sense of this equation, in particular this negative sign, I find it very useful to think of flux as being in the direction of the normal vector. So for now, pretend flux is in the direction of the normal vector. So we can think of flux as being downwards because we've chosen a downwards normal vector. And flux is getting weaker, flux is decreasing. So we've got a downwards flux that's getting weaker and weaker and weaker and weaker and weaker and weaker. If you've got a downward flux that's getting weaker, that's a change in which direction? If you've got a downwards vector, but it's getting weaker, which direction is it changing in? Yeah, it's changing in an upwards direction. So we can say that delta flux is an upwards change. And keep in mind, upwards doesn't mean it's increasing. It means it's a downwards value that's getting weaker. So the change is in the upwards direction. If you look at this in terms of vector subtraction, you've got our initial value, and then you've got our weaker final value. The change from an initial large downwards vector to a final small downwards vector is an upwards change. So initial downwards plus medium upwards change equals a smaller downwards final vector. So we are going through a change in the upwards direction. So this derivative, d flux dt, can be treated as an upwards quantity. The rate of change in flux is upwards, but we've got a negative sign in Lenz's law. What does that suggest? If you've got an upwards derivative, but then you take the negative, that means what would be the negative of upwards? Downwards. It's probably best to just interpret this negative as meaning in the opposite direction. So the shrinking flux means an upwards change. So d flux dt is upwards. This negative sign means reverse that. So the delta voltage, the extra induced voltage, is going to be in effect in the downwards direction. And we can actually use the right-hand rule to proceed from there. Upwards change in flux, reversed because of the negative in Lenz's law, means a downwards voltage. And by the right-hand rule, downwards voltage means current flowing in this direction. So current is going to flow this way based on this right-hand rule. Downwards voltage really means current flowing. I guess you could say that's clockwise when viewed from above. So that's wrapping around this way. So I'm going to say we've got current flowing like this. So that's the induced current circulating around the loop. In other words, as long as the magnetic field is in the process of changing, that changing magnetic flux causes current to flow. And the faster the magnetic field is changing, the more current you get. But of course, that only lasts as long as the magnetic field is in the process of changing. As soon as the magnetic field stops changing, the current dies off immediately. You get no more current. Also, one other final check to do here. Once you've established what direction you think the current is flowing, one other thing you can check with this, if you've got current flowing in a loop, what does that current create? Any current flowing in a loop is going to create, it creates its own magnetic field. So this induced current creates its own induced magnetic field in a direction given by the right-hand rule. Curl your fingers in the direction of the loop, so the current is circulating this way, and it's going to create magnetic field in the downwards direction. So this loop of current creates its own final magnetic field in the downwards direction. That downwards new magnetic field is opposite to the change in flux we saw earlier. The final induced magnetic field is going to be in a direction opposite to the change that caused it in the first place. The upwards change of the shrinking downwards magnetic field, upwards change is opposed by the downwards final magnetic field of the induced, or caused by the induced current. That doesn't mean it cancels out, because the induced effect isn't opposing the existing magnetic field, it's opposing the change. The current and magnetic field, we are basically using a variant of the right-hand rule. The idea that if you got current flowing in a loop, if you can curl your fingers in the direction current is flowing, and your thumb tells you the direction the magnetic field is going to point. Specifically, the final magnetic field caused by that loop of current. No, there's several different variations on right-hand rule number one. In fact, it's really not so much right-hand rule number one, it's a right-hand rule of the first type, category number one. So one variation on the right-hand rule number one, specifically for a loop of wire with current, is that the loop of wire with current is going to cause a magnetic field in the interior of the loop. And you can find that by curling your fingers in the direction current is flowing, and your thumb tells you the direction of the magnetic field in the middle of the loop. That is the magnetic field caused by that current in the loop. Any other questions on that one so far? All right, then let's try out another example. This is a good example, I think, of the idea of the magnetic field changing. But we could also have a situation where the magnetic field stays the same, but the area is changing. And one common way to do that is to have a loop of wire that's basically, you could think of it as like a set of railroad tracks. If you've got these railroad tracks, just long, straight, rigid wires, and let's say they're connected over here. Maybe you've got like a light bulb, for instance, acting as the resistor. And then you have a metal bar that you can slide back and forth. That metal bar is going to complete the circuit. You get a complete loop, but by moving it, what's changing? If we just slide this back and forth, we're changing the area. So let's say we have this metal bar. A mobile metal bar that we can slide back and forth. And of course, in order to have any sort of flux at all, we're going to have a magnetic field. So let's say there exists a magnetic field already. Let's say there is a magnetic field that is pointing outwards everywhere. It's going to have to be either outwards or inwards to have a large amount of flux. Because if it was, let's say we had a magnetic field straight up, that's just skimming along the surface of the loop. It's not going through the loop, so that would be no flux at all. And of course, if you have no flux and you change the area, you still have no flux. So in order to have any change, we're going to need an existing magnetic field. And we could also define the normal vector to be perpendicular, specifically straight out. That way the angle is 0, and cosine of 0 is 1, so we don't have to worry about that. But let's say we are moving the bar to the right. So the bar is moving to the right at some speed. Let's say a constant speed for simplicity. That is going to be changing the flux, because even though the magnetic field is constant, we're assuming the magnetic field is this value, the same value everywhere. But by moving the bar, we're changing the area. So to determine direction, first of all, just the fact that the flux is changing means that we will get voltage, which means current will flow in this loop. In order to figure out direction, though, we're going to treat the flux as acting in the direction of the normal vector. Would you say that in this context, if we're moving the bar to the right, is the flux increasing or decreasing? Yeah, the flux is increasing. If you increase the area is getting bigger, and therefore the flux itself is getting bigger. So in this example, if we increase the area, and keep the magnetic field and the angle constant, then the flux is also increasing. And so if we want to establish a direction there, delta flux equals, and again, we want to treat flux as being in the direction of the normal vector. The normal vector is outwards, so we're going to treat flux as being in the outwards direction. We also know the flux is increasing. So if you got an outwards vector that grows and grows and grows, that's a change in which direction? If it's it's a change in the outwards direction. You've got a small outwards vector that grows larger and larger and larger and larger. It's getting more and more outwards. So the change in flux is going to be in the outwards direction. So the change in flux is outwards, and here's where we want to start using the right-hand rule. And I would just use your thumb as the direction of the change in flux in this context, because that's going to ultimately be the magnetic field caused by the current. We've got an outwards change in flux, because it starts off small outwards and gets larger and larger and larger. So that's an outwards change, but we've got a negative sign that reverses it. So the induced effect is going to be inwards. And based on the right-hand rule, inwards means curling this way. So the outwards change in flux, reversed because of the negative sign in Lenz's law, suggests current circulating this way. So I guess I would call that clockwise when viewed from this perspective. We're going to get current circulating this way. That would be the induced current. Any questions on that direction so far? And in this particular context, we could even calculate how much voltage and therefore how much current using Faraday's law again. We know that the flux is area times magnetic field times cosine of 0, which is just going to be 1. And magnetic field, we're assuming, is just some constant, but the area is changing. However, the shape we're creating is just a rectangle. What's the usual formula for area of a rectangle? Yeah, length times width. Or in this case, let's say height times width. So the height, let's say we call the height y, and the width, let's say, is x. So area would just be x times y, and then multiplied by the magnetic field. So the flux is x times y, the height, or the width times the height, times the strength of the magnetic field. But we don't care how much flux there is, we just care how fast it's changing. So that means we're going to need to take the derivative of this. But what's the only part of this that's changing as time passes? You move that bar, and which one of those variables is going to change? Yeah, x is changing. As you move the bar, the length, x, or the width, I guess you could say, the width of the rectangle is getting larger and larger and larger. But the height is just the distance between rails, and that's not changing. And the magnetic field is uniform, same value everywhere, so that's not changing either. So y and b can be pulled out as constants, and we're left with just dx dt. But dx dt is just the derivative of length. What do we call the derivative of length? What do we call how fast length or position is changing? What's the term we use to describe how fast a distance is changing? That is distance over time. Yeah, that's literally just the velocity of this bar. So dx dt, distance over time, we can replace with the velocity of the bar. So that means d flux dt, and therefore the amount of voltage you get is distance between rails times strength of the magnetic field times how fast the bar is moving. The further apart the rails are, the more voltage you get. The stronger the magnetic field is, the more voltage you get. And the faster the bar is moving, the more voltage you get. That tells you the voltage. And the negative sign I would ignore here because that just tells you direction, and we've already found the direction. If you wanted to turn that voltage into current, how do you convert voltage into current? We can treat the light bulb as a resistor, right? Yeah, you just divide by resistance. The delta voltage for a resistor is negative IR. Again, I'm going to ignore the negative because that's just talking about direction, which we've already established. This is our delta voltage. We divide that by R, and we get the induced current, which is the voltage, separation of rails times magnetic field times speed, divided by resistance. So that would tell you, in this case, how much current you get. And then you could also use that with any of the formulas from 7b, like for instance, power would be I squared times R. Square this, multiply by resistance, and that would tell you the power, how bright the light bulb is, how much energy is being dissipated per second. But the important thing here is you can use the changing magnetic effects to create voltage, even though there wasn't any. This induced voltage caused by the changing magnetic flux acts like a tiny invisible battery in the loop, causing voltage just by changing the magnetic effects. Any questions on that flux idea? All right, then that's it for now. Please fill out that end of quarter evaluation survey when you get a chance, and I will see you in the review session.
Thank you, Casey.
You're welcome. Glad I could help.
Thank you.